Hi everyone. So in this video we are going to discuss about some theorems on probability. So we know what is a probability and we have seen in the previous videos what is a mathematical definition of probability or the classical definition of probability and the axiomatic definition of probability. So now based on the axiomatic definition of probability we are going to discuss some theorems on probability. So this is the first theorem. The probability of an impossible event is 0. And we denote the impossible event by phi. So the theorem is like this. The probability of phi is 0. So in order to prove this probability of phi is equal to 0, we consider this as the proof. The impossible event contains no sample point. That we know that the impossible event is no sample point is there in that impossible event. And we know the certain event, the sample space, the capital S is also there. And this certain event and the impossible events are mutually exclusive. Why? Like one is impossible, the other one is certain. So they can't happen together. Or for them, there is nothing in their intersection. So if I take the union of the certain event and this impossible event, S union phi, that will obviously be the certain event S. So which implies on giving it the probability terms, we can say that probability of S union phi is equal to probability of S. So we have discussed the axiomatic definition of probability in the previous videos, using which we can write probability of S union phi as probability of S plus probability of phi, which is equal to probability of phi. So it is just like we can write the union as the summations. So from there we get probability of S plus probability of phi is probability of S. That means probability of phi must be 0. Now we are going to discuss a second theorem based on the axiomatic definition of probability, and which is this. The probability of the complementary event A complement of A is given by probability of A complement is equal to 1 minus probability of A. So this is the theorem, and that means probability of A complement can be written as 1 minus the probability of A. We are all familiar with these terms and we have used this, but this is the theorem and the proof related to this. So coming to the proof, we know A and A complement are mutually disjoint events or mutually exclusive events. So A and A complement will not have anything in common. So if I take A and A complement, since A is the only event, so A union A complement will be S, the certain event of the sample space. So A union A complement is equal to S implies probability of A union A complement is equal to probability of S. So since probability of A union A complement is equal to probability of S, and we know probability of S is equal to 1 using the axiom 2 of the axiomatic definition of probability. So the probability of S is equal to 1, and using the axiom 3, that is the axiom of additivity, we can write probability of A union A complement as probability of A plus probability of A complement. So from there we will get probability of A complement can be written as 1 minus probability of A. So this is a theoretical proof for this complement. How we write probability of A complement as 1 minus probability of A. So this is a third theorem. Here we have two events A and B, and those are not disjoint events. They have some common points too. So the green picture, in the Venn diagram, the green circle is what is A, and the blue one is A, B, and their intersection is A intersection B. So the theorem is as follows. For any two events A and B, we have probability of A complement intersection B is equal to probability of B minus probability of A intersection B. So that is visible from this Venn diagram itself, that we can see the green circle is A and the blue circle is B. So that B part, B is what is A intersection, B is there, and A complement intersection B is there. Together that like A intersection B and A complement intersection B will give us the B. So the proof is as follows. From this Venn diagram we can write B as A intersection B, that is the intersection part, union the rest, that is the A complement intersection B. So this part which is not in the intersection and which is the blue one is called A complement intersection B. So we can write B as the union of these two, the intersection and the non-intersection part. So giving it the probability terms, that is B can be written as A intersection B union A complement intersection B. So probability of B is equal to probability of A intersection B. The union can be written as plus. So probability of A intersection B plus probability of A complement intersection B, since this A intersection B and A complement intersection B are disjoint. Only since both these areas are disjoint, we can write these probabilities as just the sum. So from there we will get probability of A complement intersection B is equal to probability of B minus probability of A intersection B. So this theorem is clearly visible from the figure, and it's just a theoretical proof that I had given here, that is purely based on this Venn diagram. So similarly we can prove probability of A intersection B complement, which is equal to probability of A minus probability of A intersection B. This is also proved the same way as the first part, where we use the same axiom of the axiomatic definition of probability to prove it. And here we can write A as A intersection B union A intersection B complement. And from where applying the probability and using the addition theorem of probability, or using the axiomatic definition or the third axiom of the axiomatic definition of probability, we will get probability of A intersection B complement is equal to probability of A minus probability of A intersection B. So this is a fourth theorem. This is somewhat different from the other ones. Here, this event B is a subset of event A. So if event B is a subset of event A, then we have two subsections. The first one is probability of A intersection B complement is equal to probability of A minus probability of B. And the second one is probability of B is less than or equal to probability of A. So the bigger circle, the bigger one is the event A in the Venn diagram, and the olive green, the inside part, is the event B. So denotes the event B. So you can see that the concurrent circle around it, around the B, that dark green color is A intersection B complement. Since that totally it is A, and inside which we have a subset, as a subset we have event B. So A intersection B complement is the other part, and we can say B and A intersection B complement are mutually exclusive events. So since B and A intersection B complement are mutually exclusive events, I can write A, the event A, as B union A intersection B complement, isn't it? Yes. So which implies probability of A is equal to probability of B union A intersection B complement, and probability of A union B can be written as probability of A plus probability of B, say if those are disjoint. So here B and A intersection B complement are disjoint. Therefore, I can write probability of A as probability of B plus probability of A intersection B complement. Therefore, we can write probability of A intersection B complement as probability of probability of A minus probability of B. So the next one is probability of B is less than or equal to probability of A. In this case is what we are going to consider when B is a subset of A. So when B is a subset of A, we have already seen that probability of A intersection B complement is equal to probability of A minus probability of B. And we know this probability value is for sure a non-negative value. So it is greater than or equal to 0. So we can write probability of A intersection B complement is greater than or equal to 0, which implies probability of A minus probability of B is greater than or equal to 0, which we have proved in the first part of the theorem. So we have expanded the left hand side. So probability of A minus probability of B is greater than or equal to 0, which means probability of A is greater than or equal to probability of B. That means probability of B is less than or equal to probability of A when B is a subset of A.